Moving right along in Chapter 3, we are going to continue with the idea of polynomials and be able to use some of the things we've worked in 3.1 and 3.2 to be able to graph some of these polynomials, as well as write some equations of these polynomials with higher powers. So we're going to use this section to continue learning about graphing polynomial functions which have powers higher than 2. Let's review a couple concepts. So at the very beginning of Section 1 of Chapter 3, we were looking at some even and odd degree powers and what the behavior of those looked like. So if you recall on an even one, those even ones always kind of took on the shape of that y equaling x squared. Maybe I put y equal x squared in there for you. That x squared graph, which as a reminder, ended up kind of having in the same direction. It was a u was the x squared. But the idea is for any even power, if I have that going up into infinity in both directions, it doesn't really matter kind of what goes on in between here. The end behavior has to go up in both directions, as long as a is positive. Now, if we had a negative in front of our x squared, remember then if a is negative, we end up having kind of the behavior where it's going down. We can bounce around inside there, but the ending part will also go down as well. So, for a equaling positive, I'm going to kind of just recognize the end behavior of this one. As x goes to negative infinity, then as x goes this direction, our function goes to positive infinity. So f of x goes to positive infinity. If I'm going to positive infinity with my x, if we think of it kind of on a graph, then my f of x also goes to positive infinity. So we worked with that on end behavior out of Section 1. If we had an odd degree function, we said that it looked like that x cubed function. Okay, and x cubed, as long as a is positive, started down here, came up, we can kind of bounce around inside here, and it goes in the opposite direction when we have that odd power. So as x goes to negative infinity, as I go this direction with x, my f of x goes to negative infinity. And if I have x going to positive infinity, so in this direction, my end behavior for my function goes to positive infinity. So here, this tells me right here that those are in opposite directions. Now, if a is negative on your function, remember then that your graph is reflected over the x. So it does something like this, bounces around and eventually goes down to negative infinity when x goes to positive infinity this time. So make sure that you remember those patterns and that type of thing so that whenever we're working with higher powers, you have to remember, is it even, is it odd? Now, we in Section 3.2 also looked at reminding ourselves what happens when I try to find a Y-intercept and an X-intercept. Well, it is kind of opposite. If I'm trying to find the Y-intercept, I let x equal 0. If I'm trying to find the X-intercept, I let y equal 0. So we will have some practice on some of those. And this first one actually is practice of just that. So we were looking at a function now in terms of c and t. Well, don't let that throw you off. If it is finding C-intercepts, remember, it's kind of the opposite. You let the other piece equal 0. If I'm finding the X-intercepts, I let the other piece equal 0. So here when I'm finding the C-intercept, then that's acting kind of as the y value. Then we're going to let t equal 0. So wherever I see a t, I'm going to plug in a 0. So c of 0 is equal to 2 times 0 minus 4 times 0 plus 1 times 0 minus 6. And now I just have to multiply this all out. First, obviously, simplify the parentheses. So I get a negative 4 here. I get a positive 1 and a negative 6. So when I multiply all of those together, our C-intercept is actually a positive 48. That would be acting kind of like the Y-intercept as well, okay? Now, when I ask to find the T-intercepts, then again, we let the other piece equal 0. So this time we're going to let C equal 0. And so when I let C equal 0, that means that 0 has to equal 2 times t minus 4 times t plus 1 times a t minus 6. Now, We just did that in our factoring section where we were given, most of the time it was just 2 of these parentheses, but we can have multiple ones of those. And we want to go down the line by the zero product property and say what makes each one of those zeros. And that would kick out a root or a solution or a T-intercept in this case for this function. So first thing I encounter is a 2. Can 2 ever equal 0? The answer is nada. It's not going to kick out an answer if I just have a number out front. If that was a T out front, absolutely, it would give me 0 as an answer. But as it stands, this does not give us a root. So what number minus 4 is 0? That is 4. What number plus 1 is 0? That's negative 1. And what number minus 6 is 0? That is a positive 1. So those are your T-intercepts, and this is your C-intercept for that. Again, remember, just let the other one equal 0 if it's some other letters besides x and y. All right, let's get back to our x and y's. Given a function, f of x equals x cubed minus x squared minus 2x. We want to find our y-intercepts. We're going to let x equal 0. And our x-intercepts, we're going to let y equal 0. And then we're going to talk about the end behavior of this function. So kind of put some of those two things at the top together. All right, so if I'm trying to find the y-intercept, I want to let x equal 0. So in that sense, I need to look at f of 0 equals 0 cubed minus 0 squared minus 2 times 0. Well, that's a lot of zeros in there, and it's pretty boring because this is 0, that's 0, and that's 0. Therefore, f of 0 equals 0. 0 is our y-intercept in this case. Okay, 0 is the y-intercept. Now, what about our x-intercepts? We want to let y equal 0 for our x-intercepts. Well, what is y? I don't see y, but remember that that function notation is the same as y. That's our output. So I get, and actually I'm going to reverse the sides. I'm going to write this first and set it equal to 0. We can do that. So let's do x cubed minus x squared minus 2x equals 0. All right, now, unlike the first problem that we just did up here with our C of t, I already have factored form. This is not factored. So from our section of factoring, we want to ask ourselves, is there anything in common? And there's an x in each term. So I'm going to factor out an x, and I'm going to take away an x from each term. So that leaves me with an x squared minus an x minus a 2. Now remember, if you get a power of 2, you really need to work on seeing if that can go further. So if I can make that go further with that trinomial, it will factor down into 2 binomials. Check out your last sign. The last sign is a minus, therefore one's a plus and one's a minus. Split up your x squared as an x and an x. And because I have this nice invisible 1 in front right there, what do we multiply to get 2 that we subtract to get the invisible 1? What do we multiply to get 2 that we subtract to get 1? Well, since 2 is prime, it's the only even number that is prime, the factors are 2 and 1. Well, we subtract those and we get 1. But notice I need a negative 1 there. So the sign is very important when you have different numbers or different signs inside there. I do need a negative 2 plus 1 to give me that negative 1. So again, if you were to FOIL this, you would end up getting this term back. All right, now we're ready to go to find our x-intercepts. We go down the line and say, okay, what makes each one of these equal to 0? Now notice I have an x now on the outside. What number do I throw in there to make that 0? And again, don't make that too hard. It is 0. What number plus 1 is 0? We just had that on the previous problem. That's negative 1. What number minus 2 is 0? That number is 2. So therefore, these are my x-intercepts. But I've modeled kind of what it would be doing in my open math so that you can see what they're doing. This is just asking you to go from the smallest to the biggest. So x1 is less than or equal to x2, which is less than or equal to x3. So the smallest of these 3 is negative 1. Then I would do 0. Then I would do 2. And those are my x-intercepts. Now, our last thing that we have to do is our end behavior. End behavior comes back to our original function and looks at the degree of that function. Now, the degree of that function is the highest power. which we went over in section 1. It is the highest power, and so the highest power of this function is a cube. So the degree is 3, and if it is a 3, that means it's acting like, it's an odd, so it would be acting like an x cubed. So what would the end behavior be? So as I'm going to negative infinity with my x, my f of x is going to negative infinity as well. Oops. F of x is going to negative infinity. If I'm going to x going to positive infinity, then the f of x is going to positive infinity as well. So remember, with odd powers, your end behavior, they better be opposites of each other. One must be a minus and one must be a plus. Okay? If it's an even number, those would be the same. They would either be both negative infinities or both positive infinities. Okay? So, let's look at the next problems. We just have to do our end behavior. So what's going to be important for us to know is this piece right here. It all depends upon the degree of that. Now here we have lots more powers and lots more factors, okay? So the degree of this polynomial is basically going to be, well, in this factor I only have 1x. This factor I have actually, notice here I have 2. So actually I can account for the 1x here on the power. I get 2 x's from here if I were to FOIL it all out, and I would get an x cubed from here if I were to FOIL it all out. So I get 3, 4, 5, 6. That degree is 6. Now look in front. A is positive. So if I have an even power, it's going to look like my parabola, and my end behavior goes in the same direction. With A being positive, it's going to be going to positive infinity and positive infinity. So here's what we would write. As x goes to negative infinity, my function goes to positive infinity. F of x goes to positive infinity. As x goes to positive infinity, the end behavior also goes to positive infinity, and they are in the same direction. Okay? It's all dependent upon that a value and the power. So this would be your final answer. Now, My Open Math actually gives you some drop-down menus that you can use in order to put the infinities in there, okay? Next one, how many x's do I get? What would be the degree of that polynomial? Well, notice here, I have a power of 1 out front. I've got a power of 3. I've got a power of 1 and a power of 2. So 1, 4, 5, 6, 7. The degree is 7. But notice out front now, here's my a value, which is less than 0. It's negative here. So we want to make sure that we remember for an odd power, normally it goes like this, like we just saw, but we don't want that. We want the reverse of that, okay? So the negative does something like that. So what does our end behavior do? As x goes to negative infinity, what does f of x do? And as x goes to positive infinity, what does f of x do? All right, so here, if I go x to going to negative infinity, my function goes to positive infinity. If x goes to positive infinity, my function ends up going to negative infinity. So with an odd degree, these have to be different. For an even degree, these have to be the same. Okay? All right, very good. And the last piece here kind of puts this together with all these powers that I have here on these problems. Those powers are what we refer to as the multiplicity of a term. How many times is it multiplied together is another way to think of it, okay? The multiplicity of a term identifies basically the power, how many times it occurs, and this is going to be helpful when we are going to problems that look like such on your next piece of paper when writing the equations, okay, and knowing the multiplicity. That gives me the power. So find the equation of a polynomial of degree 6. So all my powers better add to 6. We have a leading coefficient of -1, which is actually my a value. And we have multiple roots. I have 1, 2, 3, 4 roots. But notice these have multiplicity of 2, and these have multiplicity of 1. Okay? Remember, multiplicity, aka, is the power that goes within that binomial. So remember when we're finding these roots, if I go back to this page and I scroll down, how did we get the 0, the negative 1, and 2? I had this in my equation with those binomials, x plus something, x minus something, and also if I needed 0, remember that x was out front. So that's what we need to create for this function, okay? So p of x is what we need. Now, the leading coefficient is negative 1, so I need that out front, definitely. With a root of 0, remember, what did we have to have in our equation to kick out a root of 0? We just needed an x. So I need to throw an x down for that. But what is its multiplicity? Its multiplicity is 2, so that means it occurs twice. So I need a power of 2. What had to be in my parentheses in order to kick out 5 to be an answer? Well, remember, we ask ourselves, what do we add or subtract inside here to get that to equal 0? So in that case, we end up having to have an x minus 5 here to kick out a positive 5 for the root, because when I throw 5 in there and subtract 5, I get 0. But what is its multiplicity? Its multiplicity is 2. Turning to this root of negative 2, inside the parentheses, we have to kind of see the opposite of what that sign is, and its multiplicity is 1. So you can write a 1 there, but you don't have to. It can be invisible. And our last one, likewise, should be an x plus 1. Multiplicity of 1 could be invisible, or you could end up writing that 1 as well. So that would be our final answer for that function. Okay? All right, now let's try this next one. This time we kind of cut the degree in half. Now we only have a degree of 3, and I have a root of x equaling 1 with a multiplicity of 2. So that means that I had to have an x minus 1 in my parentheses. Multiplicity of 2 means I have to square that. And coming over here, I have a root of negative 3, so that means I have to have an x plus 3 inside there. Multiplicity of 1 gives me that power. Now, unfortunately, I left off this piece this time. We didn't explicitly tell you what a was equal to, but don't panic, we can find it. So our polynomial p of x, or our function p of x, has to be of the form where I have some number out front, could be 1, could be negative 1, could be a half, could be 2, all kinds of things. But then I have my factors here to kick out my roots with each of the multiplicities. Now, the extra piece they gave me on this problem is this point 210. Remember, that 210 is an x and a y value that satisfies the equation for my polynomial. So what do we have over here? Here's my x value. And remember, this function notation represents the y value. So what I can do to solve for a is to plug each one of these values in for x and for y. So the y value is 10. I'm finding a. When x is 2, don't forget to square it, and I'm going to plug in 2 in 2 places. So I just need to figure this piece out. Let's simplify that. Well, 2 minus 1 is 1. 1 squared is 1. And this gives me 5. So 5 times 1 times a, 5 times 1 is 5. 5 times a is 5a, equals that 10. And now I can divide nicely by the number next to the letter and find out that a equals 2. Now, when I get done with that, we need to plug that right back in there to write our final answer. So p of x is equal to 2 times x minus 1 squared times an x plus 3. And that would be our final answer there. Okay? All right, very good. So that's kind of going through the in behavior, how to find intercepts, how to go backwards and find that equation. Now, what if we have that equation? What's going to happen graphically for these polynomials that have higher powers bigger than 2? So, coupled with in behavior multiplicity of roots will help us determine the look of the polynomial graph. Let's look at this example. So I give you this function and I give you the graph of that function. Notice that if I say, okay, what makes this piece 0? Hopefully you tell me negative 3. What makes that piece 0? Positive 2. What makes that piece 0 is negative 1. Here's negative 3, negative 1, and positive 2. Okay, so let's look at which of those has the multiplicity of 1. Well, it's this guy with the power of 1. What is happening at negative 3? With that graph, it's coming down, and it basically just goes through that axis. We just go from positive to negative, and then we kind of turn around. So we call that a cut, that it cuts through the intercept, going from a positive to a negative, okay? Anytime you have a power of 1, your graph will look like this. Nice straight line through that intercept. Now, looking at multiplicity of 2. There's my power of 2. That is for the x-intercept of 2, which is this guy right here. And I look at the behavior of the graph around that intercept. So notice I'm coming down, and I get to 2, and I go back up. Well, layman's terms, we refer to that as that the graph bounces at that intercept. Comes up, and it bounces off that axis. Whether or not it comes down, and it bounces and goes back up, or it comes up, and it bounces and comes back down. Either way works. And when we have a power of 3 for our multiplicity of 3, that is at my intercept of -1. So if I look over here, what happens at -1? Well, notice I have this curvature here, kind of like that squiggle of an x cubed, okay? So the graph looks like an x cubed at that point, where we just kind of flatten things out a little bit. It's not going straight through, but we flatten it out a little bit. So here's what happens when we get higher powers. We're not going to work too much over 2s, 3s, and 1s. But if you were to get up into the 4s and 6s and 10s as powers, the graph will still end up, let's see, for even powers we bounce. So it still bounces off of the x-intercept, but the graph will appear flatter with each increasing even power as it approaches and leaves the axis, okay? So instead of something that looks like that, it may come down and kind of do something that looks like that, okay? Now, if we have an odd power, for higher order odd powers, we are still going to cut through that intercept, but the graph again will be flatter at that intercept when we increase those odd powers. So when we get to 7th, the 11th power, all of that kind of stuff, then we flatten it out even more so here, where it ends up doing something like that, okay? All right, so can we graph this? Can we just do a sketch of these equations that we have? Now, we're not going to get too specific here. In some cases we are, but we're not going to get some specifics on like our max and min pieces. Now, in order to be successful to do this, you have to determine your degrees. We're going to determine our degrees, we're going to determine our x-intercepts, and we're also going to determine our y-intercepts, okay? So let's talk about the degree. That is basically the culmination of your powers. So just add the powers of your x's. So notice here, how many of these do I have? If I were to FOIL this, I would get an x squared. So take that 2, take this invisible 1, therefore our degree is 3. Now, what about my x-intercepts? That means I let this equal 0, and I go down the line and I say, okay, what makes this 0? That is -3. What makes this 0? That is at a +2. Now, if we're graphing, let's go as far as to saying, does this bounce or cut through at -3 and at 2? Now, what happened when we bounced? Bounced, we had a multiplicity of 2. Cut had a multiplicity of 1. So here we have a multiplicity of 2. Therefore, at -3, I'm going to bounce off that axis. And at +2, I have a power of 1. Therefore, with the multiplicity of 1, we cut through that axis. All right, one more piece of information that we like to have would be our y-intercepts. Remember, now instead of letting this be 0, I let these be 0. So our y-intercept is going to be 0 plus 3 squared times 0 minus 2. Now, what do we get there? Simplify inside, do any exponents, and then multiply. So 0 plus 3 is 3, squared is 9. This gives me a -2, so 9 times a -2 is a -18. So that's where we're going to cross our x or our y-axis, excuse me, at -18. All right, so we're just going to kind of do this sketch here. I'm doing that -18 because if I'm crossing at the -18 on the y-axis, it's going to be down there somewhere. I also am going to cross now on my x-axis at -3 and at +2. So I'm going to put those points on there as well. Now, remember, a degree of 3, A being positive, that means I end up having that squiggle that goes in that fashion. Starting down here, I'm going to increase. Now, what happens at -3? We bounce. Okay, so I come up and I touch that intercept and I come back down. Now, in order to get back up here to this intercept, number one, I have to come through -18. And when I come through this intercept, what are we doing? At +2, we're cutting through that intercept and going off to infinity. Now, does it have that end behavior where I'm going to -infinity on the left, +infinity on the right, -infinity on the left, +infinity on the right? Yes, we are. So that would be a sketch of our graph for this function. Now, obviously, if you want more specific points, you can plug in those points to figure that out. Okay? All right, let's change a color so we can see the difference here with these. I know which one's which. Let's look at the degree of this guy. So adding my powers of x, there's a 1, there's a 1, there's a 2. So we would end up having 2, 3, 4, degree of 4. You might think it is an upward, like a U shape, but notice out front we have a -3. Therefore, it's going to have that end behavior of going down and down. Let's talk about our X-intercepts. We're going to go down the line. What makes that 0? What makes that 0? What makes that 0? So this, remember that letter out front, what makes that 0 when I throw in for x and times by -3? It is 0. What number plus 2 is 0? It is -2. What number minus 4 is 0? +4. And so now, looking at our multiplicities, does it cut or bounce at each of these roots? So with the power of 1, we cut at 0. Also at -2, we're going to cut, but with the power of 2 at 4, that means we're going to bounce at x equaling 4. Find our y-intercept by letting x equal 0. So I get -3 times 0, 0 plus 2, and a 0 minus 4 squared. Well, you can multiply that all out if you want to figure these things out, but I'm looking right here. -3 times 0 and 0 times whatever else this is still going to be 0. Therefore, our y-intercept is 0 here. Okay? All right, so let's do a graph. Again, we're just sketching it. I believe on my open math, you're going to be looking at some multiple choice ones to see which ones they are. We're going to be crossing on the x-axis at -2, 0, and +4. We have to start down here, and we have to end down here also. Okay, so how do we do that? What happens at -2? I'm going to cut through. So I'm going to start down here. I'm going to cut through. But notice I got to get back to this x equaling 0. So that means I'm going to go up and come back down. Now what happens at 0? At 0, I cut through. So I'm going to cut through that. I got to somewhere get a turnaround point to come back up here at 4. So I'm going to turn around. And again, you don't know exactly where that is. I'm just doing a sketch. And at x equaling 4, remember, we're bouncing off that axis. I can't cross it. So I'm going to bounce off, and I'm going to end up going in the opposite direction, okay? Go back down. Now, does that end up getting in the same direction? Yes, it does. So that lines up with that piece there, okay? All right. Let's look at our last one of these, and then we'll turn to the back side. Notice we have a power of 3, 4, 5. So this is a degree of 5. Let's find our x-intercepts. Go down the line. What happens here to make that 0? What number? It is 1. What number plus 3 is 0? It is -3. What happens with the power of 3 or the multiplicity of 3? Remember, it's still going to cut, but at 3, it's going to kind of do that little squiggle around x equaling 1. And at -3, I have a 2, so we're going to bounce off that axis at -3. Excuse me. All right. What is our y-intercept? For our y-intercept, we're going to let x be 0. So 0 minus 1 cubed and a 0 plus 3 squared. This is a -1 cubed. Well, that's still a -1. And this becomes 0 plus 3, which is 3 squared is 9. So 9 times -1 is -9. Now, with a degree of 5, remember that's like an x cubed. It's going to in opposite direction. So we're going to start here and go there. It is an a value that is positive, so it is in this direction, okay? All right, so let's do a sketch. We have intercepts at -3 and at 1. And we have a Y-intercept at -9. So I'm going to throw that down there. All right, so where do we start? For next to the 5th, with A being positive, we're going to start down here and go up. So I'm going to kind of start down here. What happens at -3? Remember, -3 we bounce. So I'm going to go up and bounce off of that. But I have to come down, and it's nice and smooth. I'm going to hit at -9, go through that intercept. And then at 1, remember I need that squiggle. So this is going to be a little bit tricky. I'm a little bit thin. I'm going to kind of do something that looks like that. So I can get that little squiggle in there and show that. So I kind of I need to kind of make, and actually in reality it's probably doing more so like that. Instead of having that piece right there, we can erase that off. Oops. That piece right there. Let me fix that for you. Okay, and again, we're just sketching. It's not like we know exactly where it's at, okay? So that would be our intercept right there, okay? All right, very, very good. So turn to our back side here. Now we're going to take these graphs and write equations of those. So notice we have to identify our intercepts, which are right here for this one. We have to throw them into a function form, okay? Where, what do I have to have in my parenthesis to get -3 as an answer? Has to be an x plus 3. Then for -1, I have to have an x plus 1 in my equation. For +2, I have to have an x minus 2. They're all opposites, don't forget. And then we have an x minus 4 in there. Now remember, we have to end up looking at our multiplicities. So it cuts through here, cuts through there, and then I end up bouncing and cutting. All right, so now once we decide on our multiplicities, then we can add our powers in. So this cuts through, so I have to have a multiplicity of 1. You can put the 1 or you don't have to. This also cuts through, so I have to have a power of 1. But when I get to my +2, remember I'm bouncing off of that, so that would be a squared. And then I end up cutting through here, gives me a power of 1. Now, one thing I can't forget is this A value, okay? You have to have that A value because I need to determine what that is. And how that I determine that is by that point right there. Choose a point. The only one that I know nicely here is the point 0,3. Okay? So, I have an X, I have a Y that I can plug in and solve for A. So this is my Y value. Plug in for your f of x. I'm solving for A, and I'm plugging 0 into all these x's. And when I do that, now I have the capability of being able to find out what this product is, which then I can divide that out. So here we go. 0 plus 3 is 3, times 1 is 3. This gives me a -2 squared is 4. So 4 times 3 is 12. And 0 minus 4 is a -4. So multiplied together gives me a -48a equals a +3. And when I divide by -48, then I can reduce that A value. So 3 over -48 is actually -1/16 reduced. And so I can plug that right back in here and get my final answer. So f of x is -1/16 times x plus 3 times an x plus 1 times an x minus 2 squared times an x minus 4. And that's your final answer. My watch is talking to me. All right, let's try another one. So here we have 3 different intercepts. We have -3, -2, +1. So that means in my function, I need a binomial for each one of those. So if -3 is an answer, x plus 3 is a binomial. Also, x plus 2 is a binomial from the -2. And our +1 kicks out an x minus 1 in that equation. Now, we have to remind ourselves of the multiplicity. Each one of these are cutting through, therefore they are powers of 1. This guy ends up having that little squiggle, hence this then would be a power of 3. Now, all that's fine and dandy, but we can't forget about A. And how are we going to find A? Well, we need to find some other point on this function. Unfortunately, there's nothing, we can't use our intercepts, and there's no other point that we really know about until we look at the y-intercept. So 0, -1 is the x and y value that we're going to plug in. 0 is always nice because it makes this piece easier. So -1 goes in for f, that's our y, equals a times 0 plus 3 times 0 plus 2 times 0 minus 1 cubed. So now we need to multiply all this together. 3 times 2 is 6 times a -1 after I subtract and do that gives me a -6a equals -1. And when I divide by -6, a here is 1/6. So that is what I'm going to put right up in here. And our final answer is f of x equals 1/6 times x plus 3 times an x plus 2 times an x minus 1 cubed. And that's our equation. Okay? All right. Very good. So our last topic that we have within here, it's nice that we lead into these inequalities from the graphs, because now, instead of looking at equaling to 0 like we've done in the past to find our roots, we are now looking at a region of values. So where things are positive, the y values are positive, and where things or the function is negative is what we're looking at. So you're going to kind of, in a sense, divide your axes across the x. If I'm looking for positive values, I'm going to look at all of the graph that's above the x-axis. If we're looking for when it's less than 0, we're going to look at everything that is below that x-axis. All right, so here's the equation for our graph. It is negative, so it kind of starts at the positive, comes down, goes negative. And if I ask to solve this inequality, where is my function, where is f of x, I could also replace that, greater than 0. That means we are looking for when that function is positive. All of this is in the positive region. Now, we're doing this in relation to the x-axis, and that's what makes it kind of tricky. Everything in this function is positive in this area. For the x value that corresponds with that, that means we're looking at everything from -infinity until I get to 2. So we're doing interval notation again to symbolize from -infinity to 2, that function is positive. Now, I'm going to do a parenthesis here because there's no equals on that greater than 0. Now, if asked when our function here, which is the same as that, is less than 0, then that means I'm looking for when we are in the negative region. So here, my function's in the negative region forever and ever and ever. So that means it's starting at 2 and going in this direction is when we are negative. So again, no equals on our inequality, so I need a parenthesis here. Going to positive infinity, and that infinity always has a parenthesis. Okay, so we're going to kind of use that idea of sketching these graphs to be able to determine where our function's positive or negative, in this sense right here. So we're going to do 5 steps of that. First, we want to make sure that 0 is on one side. If the function is not factored, you want to factor that so we can get our intercepts across the x-axis. Then we are going to determine the x-intercepts. We're going to check the region that we need, whether we need a positive or a negative, and we are going to pick the correct sign that we need. Where is it positive for greater than or equal to 0? Where is it negative for less than or equal to 0? Okay? All right, so let's go through this. How would I graph this? We're going to again look at the degree. Think about that. There's a power of 1, 2, 3, 4, 5, 6. So that degree is a power of 6. A is positive, so that means that I'm going to act like a positive x squared and go up and up. So let's get a sketch on here. Actually, let's find our roots first. Let's find our x-intercepts. Roots, x-intercepts, same thing. What makes that 0 is 0. What makes this 0 is -1. What makes that 0 is a positive 3. Now, by our multiplicities, what happens at each one of those zeros? So we have a power of 1. That is going to cut at 0. Power of 2 means we're going to bounce. Power of 3 means we're going to end up having that little squiggle at that piece, okay? So this gives us kind of all the tools we need to be able to, and I'm going to just, just do some points. I'm not going to do the full two-dimensional. We're just going to kind of think of it one, well, we kind of are going to sketch it, but then we're going to come down to one-dimensional to give our answer. All right, so if we are starting with a power of 6, we're going to end up coming from the top. At -1, notice I bounce. So I'm going to kind of bounce here. But I have to come back to 0 and cut through. So I'm going to cut through, but when I come back to my x at 3, I have to do that little squiggle. So it's going to do something that looks like that. So that's kind of what the graph, in a sense, is really kind of doing. Again, it's just a sketch. But what are we looking for? We want that function to be less than 0. Well, less than 0 means I have to be below that x-axis. So the region that I see that is below that x-axis is this piece right here. So bring it down into the x's. It is negative between 0 and 3. I'm opening those circles because there's no equals. So the region that is my answer for this, when I ask to solve the inequality, is the x values at which our function is negative, which is down here. And that would be your final answer. Okay? Let's try the next one. We have 0 on one side. We have to factor the polynomial completely. Notice I have a power of 2 on the inside this time. Up here, we had powers of 1, and I forgot to check that piece. But we have power of 2 in here. So can I go further with this binomial? Well, it is a difference of perfect squares. Therefore, the answer is yes. I can factor that one more step. So in our factoring section, we had 1 a plus, 1's a minus, x and x. And what did we square to get a 1? It was 1 and 1. So that was the binomials that were exactly the same except for 1's a plus and 1's a minus. Now, what is the degree here? If I look at my highest powers or count my x's, 1 power, 1 power, 1 power. So 1, 2, 3. The highest degree is 3. A is positive out front. So therefore, I'm going to do something like that. Let's find our x-intercepts. The x-intercepts happen at -7, -1, and +1. -7, -1, and +1. Now, what happens at each one of those? Well, with powers of 1, 1, and 1, we cut, cut, cut. Okay, so let's see what happens. I'm going to one-dimensionally throw on those roots. So I'm going to have -7, -1, and +1. Because it's a degree of 3, that means I'm going to start down here, and I'm going to cut at each one of those zeros. So I end up doing something like that. And we are concerned with, for this inequality, where the function is greater than or equal to 0. So that means, where is it positive? So I'm looking at everything above that axis. So that's here and here. So I need all of these x values, and I need all of these x values, but because I have an equals back here, I'm going to throw solid circles on each one of those. Now, in interval notation, instead of parentheses, now we need our brackets. So from -7 to -1, and from +1 to infinity would be our answer. And those are the regions that give us our final answer there. Okay? All right, last one. Notice this one we don't have 0 on one side. I have a power of 3, a power of 2, a power of 1. So I'm going to go in descending order, but I need to subtract that over. So I end up with a -x³ plus 4x squared minus a 4x less than or equal to 0. So we're looking for negative regions here. Okay. So we have to factor it now. Notice that there's an x in common, and actually this one's negative. So I'm going to choose to bring out a negative x. Well, if I bring out a negative x, I'm left with just an x squared. If I take a negative away from there, I have to leave a negative. Okay, so negative times a negative becomes a positive. So basically when you take a negative out, you're just changing the sign. And I have to take one of those x's, so I get a -4x. Take a negative out, which changes that sign, and take the x with it, so I just get a +4, and then we have less than or equal to 0. Now, with the power of 2 inside there, can we go further? Well, when it's a trinomial, we're going to try that binomial times a binomial. Last sign is a plus, so they are the same that match the first, so minus, minus. Split your x squared as x and x. And what do you multiply to get 4 that you add to get 4? Well, that answer is a 2 and 2. Now what do you notice here? This ends up giving me the same answer. Therefore, I can write it as a power of 2, aka a multiplicity of 2, and that would tell me that I need to bounce at that root. So let's see what we can have. Let's write it over here. What's our degree? Well, notice here, the highest power is 3. So if I look at my factors, there's 1, 2, 3. So highest power is 3, but I have a negative out front this time. So that means it's going to do something like this. Our intercepts this time go down the line. What makes this 0 is 0. What makes this 0 is positive 2. Because I have a power of 1, it cuts at 0. Power of 2 bounces at 2. So let's see what happens. We're going to start at the positive, go down to the negative. We need a 0 and a 2. I'm going to start here and cut through at 0. But when I come back up to the 2, I'm going to bounce and go in the opposite direction. So there's my graph. What values this time are less than or equal to 0? I need below the x-axis. So everything here and the corresponding x values, everything here. So that's going to be from 0 to infinity. And that would be my final answer there as to the solution for that inequality. So a lot of good stuff in this section, so make sure that you practice that. I know it's kind of a little bit longer on these last 2 sections, but a lot of good stuff in here, and it all just kind of molds together very nicely. So until next time.